Hello friends, good morning and good evening everyone. Your ALP here. So today I am here with one more guest, Mr. Tuhinanshu with us. So here, this is not the new combination. We already did one more session earlier. So this is second time we are participating on this discussion. So this is about the project, the PhD project with Mr. Tuhinanshu is doing. So this is about a MIMO converter, multiple input, multiple output converter. So the application, there are huge applications are there. And the project team is very good, so it combines all the resources. I mean, you can give number of resources at the inputs at the input side, like a PV cell, wind, and fuel cell, and like a DG set, and like a electricity from the power grid. So I mean the grid. So you can give number of inputs, and simultaneously you can take number of outputs also. For example, DC supply of a different magnitudes, like for 120 volts, 240 volts, 600 volts, whatever we need based on the application. And simultaneously the AC loads of single phase or three phase and of controlled capacities, we can get it. So this is the topology, guys. So this is a wonderful project, and I hope this project, the details we discussed is useful to you, and it will give some good ideas to you also for proceeding further. If you have any questions or comments or anything, then do comment in comment section. You also can connect with the author. The details are available in the comment section. The description of the author details are available. And if you want to be a part of this project, then you can join with us. And yeah, if you're watching this video for the first time, then do subscribe to this channel so that whenever I'm uploading videos, you will get notifications. You can simply click and watch it. Keep watching. Hello.
Hello. Am I audible?
Yes, you are audible.
Okay.
Yeah. So welcome again. Happy to see you second time.
Thank
you.
Thank you very much. Thank you.
Yeah, our last video was well received by the audience. It's good. Yeah, the concept is good. I mean, how we can use fuel cell and all. Yeah, it's very nice. Yeah. So how are you?
I'm fine. Congratulations for the baby.
Yeah. Thank you. Yeah. So 5-6 days I am off the. I mean, I'm not online. So just yesterday I am back.
Yeah.
Okay. Yeah. So you are going to share the screen, right?
Yeah. Sure.
Please proceed. Yeah.
Okay. Thank you very much.
Yeah.
It's coming that host has disabled participant screen sharing.
Now we can do.
Okay. Is it visible?
Yes. It's visible.
Fine.
Yeah.
Okay.
That's it. Yeah. Proceed.
Okay.
Yeah.
So basically, yeah.
So
basically,
yeah. You proceed. Yeah. Proceed.
Okay. So basically today I want to discuss a project with you. So it is based on a multi-input, multi-output converter.
Okay.
We are proposing it for Indian Railways and many other applications. So basically, not only Indian Railways, we require funding for this research. We are in MNNIT Allahabad, and I'm actually doing research under Professor R.K. Singh. So we require funds for this research, and we are open to any private firm or public organization. Anyone can provide funds for this research, and we'll be doing this. Okay.
Yeah.
So what is this basically is that it's a new kind of multi-input, multi-output converter, and it is based on renewable energy, right?
Yeah.
So I shall proceed now.
Yes.
So first I'll give an idea of multi-input, multi-output converters, right? So basically they are a combination of more than one power generating systems, right? So you have a conventional power generating systems, like you use coal, you use wind power. I mean, not wind power, like hydropower.
Yeah.
To generate electricity, fine. You supply it to the grids, and then it is being transmitted to the load end, right?
That's true.
So we have basically conventional types of systems. We have non-conventional and combination of both.
Yeah.
So what we are doing in multi-input converters is that we are taking a number of inputs. Like we are not only limited to one kind of input, right? We are not, for example, if you are generating from an alternator, right? So you are mechanically moving the turbine, right?
That's
so
true.
You may move the turbine via a hydro source, okay, or maybe through a steam, fine,
Yes. Yeah.
generated by the coal, right?
Yeah.
So
okay. Yeah, proceed.
So as I was talking, there are several types of sources of energy, like we are all familiar of them.
Yeah.
Conventional, non-conventional, and many others. So in the conventional, we include coal, petroleum, hydropower, and such sources. And in the non-conventional, we say that there is PV, like solar energy, right? Solar energy, wind energy, and then tidal, fuel cell, etc. So you can also use a combination of both types of inputs. Where, for example, if you're establishing a microgrid, right? So you can use a combination of all the types of inputs. You can install a wind power plant, and then you can also use a PV nearby, and then you can supply to a local village or something like that, right?
Yeah.
Okay, and there can be different types of loads, like RLC and RL loads. Okay.
Yeah.
So talk about that. We'll come to the topic. So we are gradually proceeding. Okay. So the hybrid energy sources to load systems uses several power electronic converters. Like whenever we are using power supply, we are building a power supply, right? We are studying power systems even then we have to apply power electronic converters at several places. Like we have to use choppers, rectifiers, inverters, right? Choppers. What are choppers? They are DC to DC converters, basically. Either they are boosting the voltage or bucking the voltage, right? Or depending on the duty cycle. Then there are rectifiers, like they convert AC from AC, they convert it to DC. And then there are inverters that they change DC supply to AC supply. Okay. So basically these converters are made up of switches, power electronic switches like MOSFETs. And these power electronic switches are made up of devices like semiconductors like silicon and germanium. Nowadays silicon carbide and gallium nitride is being used. Okay. These silicon carbide and gallium nitride basically are called wide band gap devices, right? So I'll talk about them in detail in this session. So okay, so this is basically an idea of multi-port energy router. Okay, it has been proposed in a paper, in research paper, this converter, but not an extensive work has been done. We are planning to apply it in railways and do a much better work, right? So this is a MIMO converter, and energy source and the different type of energy sources have been used, like energy storage, then PV, like solar cells, then fuel cells have also been used, right?
Okay.
Then the supply is being given to utility grid and AC load, because utility grid, when extra generation is there, then the power is fed back to the utility. Power is fed back to the mains, right? So and there is AC load also. So basically the converter here after the MIMO converter here, it is a bidirectional converter, right? So then there is DC load also. So this MIMO converter, what will it do? That it will take inputs from different types of sources, and it will give outputs according to our needs, right? So whenever we are using AC loads, whenever you are using DC loads, this MIMO converter will handle everything. Like till now you had rectifiers, either you had rectifiers or inverters or choppers. So what choppers did, that they were DC to DC converters. So you would apply them where you had the need of taking input from DC and giving output to DC. Fine. And rectifiers you would use whenever you wanted to convert AC supply to DC supply. Okay. And inverters you are already aware of, we use in homes also. So you're converting DC to AC, right? So but if you have if you have one universal, like if you have a multi-input multi-output converter which can take all types of inputs, right? And then it can supply according to its own intelligence, it can supply to different types of outputs. So it will be a better option, right?
Yeah.
So that's what we are planning. And so basically, first we'll talk about distributed generation. So supplying only from the grid for meeting consumer. Actually, this video is my video is popping up in front of the text. So I'll
it's
just
okay.
minimize it.
Yeah, you can minimize it.
I'll
No issue.
minimize it. Okay,
Yeah. No issue for that.
So the distributed generation is supplying only from the grid for meeting consumer requirements, results in total independence on the grid. Dependence on the grid. Okay.
Yeah.
Like if you are supplying to the consumers just from the grid, right? So they are totally dependent on the grid supply, basically.
That's
like
true.
Whenever there will be power outages in the grid, the load end will be affected. Whenever there will be a fault in the grid at any point, the load end will be affected. Right. So if you are using distributed generation, if you are establishing a microgrid on your own, if you are not you're taking help from the grid supply at any point, then you are independent, independent grid on your own, right?
That's true.
Independent load. So integrating localized generation within the supply system near the load end reduces this dependency. It is also an advantage of reducing transmission losses, of course, because if your generation is nearby to your load end, right?
Yeah.
So transmission losses will be very less.
That's true.
Fine. Compared to the transmission losses, like you are transmitting from hundreds of kilometers, and you are supplying, generating and transmitting within 2 to 3 kilometers.
That's true.
The transmission losses will be very less. Then there is the integration of DG can cause several operational challenges in terms of control and protection of the distribution network. We'll discuss about this in later slides.
Yeah.
So this is the diagram of the smart grid. So what we are doing, what I was expressing, what I was explaining till now is that we are combining resources from wind energy, solar energy. You can see nuclear power plant also and thermal power plant.
Yeah.
So you're taking different inputs and you're supplying it to one microgrid, right?
Yeah.
Yeah. So you can see the wind power plant is also established there within the load end also. So this PV is also established there. Okay. So such type of system can be established.
Yeah.
Now we'll focus basically on the converters, right?
Yes.
So this is a case study. This research has been done under my supervisor previously. So some other person has done. This is a single input, double output converter, right? Dual output.
Yeah.
So it is a buck boost kind of converter. You have basically there's a buck converter, there's a boost converter, and there's a buck boost converter that can operate both in a buck operation and boost operation.
Okay.
Depending on the duty cycle, right? Like whenever you are depending on the pulse width of the the time for which the switch is being switched on, right, and switched off.
Yeah.
Depending on that time, it is giving a buck operation or boost operation. Fine.
Yeah.
So basically, we have already discussed what is buck and boost operation. Buck is like when you are minimizing you are converting high voltage to low voltage, right? And boost is when you are amplifying the voltage. So this converter is basically taking just one input from a DC input supply.
Yeah.
And then it is giving two outputs, multiple outputs. The topology, the design of this circuit is in such a manner that it is taking in one input and giving two outputs. Okay. It's the simplest form of multi-input, multi-output converter, right?
Yeah.
So, but here also you can note that the nature of the supply is same, right? Like you are giving in DC supply and you're taking out DC output also.
Yeah.
So the nature of the input and outputs are same, and the number of outputs have been increased.
Yes.
Right?
Yes.
It has just been done by changing the design of the network, changing the design of the circuit.
Yeah.
Okay. So there are certain mathematical expressions that were studied in the paper, right? They were derived in the paper after some extensive work.
Okay.
So this is the output across the buck boost port, output across the boost port, and inductor current.
Okay.
So okay, that's just for demonstration purpose.
Yeah.
Then this is another case study. This is a fuel cell and battery hybrid applied in an electric vehicle. Right?
Okay.
This research was also done under my supervisor only.
Okay.
Professor R.K. Singh sir. So Okay, yeah. So what they did in this was that they took a fuel cell and a battery. They took two inputs. Fine, and they supplied a single output. Here in the previous study, you would have seen that it was a single input and dual output.
Yeah.
Here, what they did that they took dual inputs and single output.
Okay.
Okay, and this is a fuel cell and a battery, and it is applied in hybrid electric vehicles. If it is a practical application seen in the hybrid electric vehicles. There you are already familiar with electric vehicles. People know that it is operated from electrical sources, right? You do not need to provide petroleum or natural gas.
Yeah.
So so basically when you are employing both the battery and the fuel cell, I mean you are using both the electricity as well as the fuel cell. Fuel cell can be the hydrogen fuel cell, or different types of fuel cells can be used.
That's true.
There are a variety of fuel cells. So any kind of fuel cell and simple battery is being used as a combination, and this type of circuit is being used. So you can run an electric vehicle on this. Fine.
Yeah.
So it all depends on the topology and the interconnection of the switches, right?
Yeah, that's
so
true.
You have developed a new topology here, and it can be used for doing this. So like a battery, electric vehicle operating just on the basis of one battery has different types of requirements, different running speeds and everything, and different characteristics. Our hybrid electric vehicles have different performance, different different abilities, right? Maybe it will maybe battery will run out. After battery will run out, it will support from the fuel cell. So it has it may prove better in certain applications. It may prove worse at certain applications. So it all depends on the type of requirement, right?
It is addition. It is actually an addition. For example, battery. Whatever fuel cell we can keep on. I mean, we can use it as a backup again for the battery. If ever whenever battery power is getting exhausted, so at the time it will power the vehicle, and meanwhile we can go to the nearby start charging station. We can charging it, and again we can use the it's so that people can easily can move with this combination fuel cell and battery. Yeah.
So we'll study about the features of this converter, right?
Yeah, proceed.
So basically what we do is that integration of sources together through a single converter to provide multiple outputs has a number of advantages, like lower size and lower weight.
That's true.
Right? This is true because if you are using a number of converters, like if you in this circuit only, if you are using a fuel cell, and for the purpose of supporting the motor with the fuel cell, you are using a different circuit. For supporting the motor with the battery, you are using different circuit, right? Then you are using more number of switches. You are using more. So the cost will be high. The size will be high. The weight will be high, right?
Yeah.
So if you are integrating it within a one circuit itself, then you may reduce the weight and the size, but it will still depend on the type of the topology that you are using, right? Because if you are designing it intelligently, then it may reduce the number of switches. However, if it is not decided, the topology, the design is not decided properly, then it may include more number of switches than the conventional design. So you need to design everything judiciously, right?
That's true.
So now utilization of renewable sources in the system reduces dependence on the grid supply. All right. Because if you are using renewable energy sources, so you're meeting your needs, meeting your wattage requirements with the renewable sources, and you're reducing your dependence on the grid supply, right?
Yeah.
So you're partially becoming independent. Then installment of distributed generation near the load end saves from transmission cost and transmission loss. We've already discussed this, that transmission losses and transmission cost has been reduced.
Yeah.
Then DG sets also make the system self-sufficient. All right.
Yes.
However, with MIMO converters, more switching loss will be incurred if non-ideal switches are considered. All right, because MIMO converters, multiple input, multiple output converters, I've already told that everything has an advantage and disadvantage. So if it is not properly decided, the topology, that the design of the network has not been properly decided, and if by some means like more number of switches are being used and more diodes and everything are being used, then maybe there will be more losses in the switches, right?
That's true.
So you have to decide everything. And then increasing ports increases the cooling requirements and similar parameters, thus increasing the size and cost of this. These are all challenges when you come to start designing the converter, right?
Yeah.
When you decide to design a multi-input, multi-output converters, all these challenges are faced.
Yeah.
So if you are increasing the number of ports, like if you decide that I'm going to increase from 1 port to 10 ports, right? 1 input to 10 input, then you will require more number of more cooling, right? And then your size and cost of the converter will increase, right?
Yes,
so
yes.
you have to judiciously think about everything. You have to optimize everything, right? Then again, see, the next point is about optimization only. That optimization will be needed to be carried out at several stages for cost, size, and efficiency. Efficiency will also be affected, right? Control will be easier because, yeah, now control is easier. Control is definitely easier because earlier, suppose, what can I say? Suppose you take an example of train only, because ultimately we'll be applying it into an electric train. I mean, a train only. So suppose you are using a train. So now you are using a different battery, a different electric circuit in every coach, right?
Yeah.
You're controlling the electrical load requirement of every coach independently at in the coach itself. So the control is distributed in every coach. You are controlling it at the coach only. So like if there are 10 coaches, there are 10 controls, then 10 staff, then 10 number of people will be needed in the staff just for the control, right?
Yeah.
But I mean, to monitor it always, right? But if you have a master control, okay, if you have a master control, a centralized control, then you can monitor it from one place only. So a multi-input converter has a master control. It will only need a control at a centralized place, right? One place. So the control will be easier. Fine.
Yeah.
And then, yeah, it will be considered in one place. So, okay, then fuel cell used on the source end as a dependable DG to supply large loads needs research so that it can be affordable. It becomes capable of supplying large loads.
Yeah.
Fine, because fuel cell has still got scope of research.
That's
right?
true.
Yeah. So because some fuel cells, if they are supplying good amount of energy, they are costly. If some fuel cells are cheaper, they are not supplying required amount of energy, right? Like I did with the microbial fuel cell. So it has still the scope of research. So we have to think like that. It should be affordable and it should be capable of supplying large loads. Then in future, these MIMO converters can be made using wide bandgap devices comprising of SiC and gallium nitride.
Yeah.
Now we'll be studying about issues in converter design. So these are the issues that come in what converter design. Development of novel topology of a converter taking multiple inputs and supplying it. Because first of all, you have to think about a novel topology, right? You have to think about how the circuit will work, how the design of the circuit should be. Because you have a conventional. So suppose you have a buck converter, right? Converter that takes in a high amount of input voltage and converts it into a low output value, right?
Yeah.
So suppose you have a buck converter, and then you have a conventional topology, like we already use the switch on one side, then diode, then inductor, right?
Yeah.
So if you have decided to design a new topology for the same buck converter, then you have to think on different aspects, like how your topology must be better than the previous topology, right?
Yeah.
So why should the world be ready to accept your new topology, right? So everything you have to understand. So just interconnecting different components is not topology designing, right? You have to consider many factors.
That's true.
So this is a major challenge. Then there is incorporating non-ideality, because everything will be non-ideal. Your switches are non-ideal, your supply is non-ideal, or your load is non-ideal. So you have to think, you have to incorporate all kinds of non-idealities.
Yeah.
Then there is a problem of intermittent nature of supply. That is I already told in second point, that whenever you are using renewable sources, right? So they tend to be very intermittent. Like whenever you are using solar energy, suppose. So sometimes there'll be clouds.
Yeah.
Sometimes there'll be very peak sunshine, right?
Yeah.
So the nature of the supply is intermittent. If you take example of wind speed, wind farm, wind energy. So sometimes the wind speed will be very high. Sometimes the wind speed will be about negligible. So it will not operate uniformly always, right? Even if you take an example of fuel cell, it will start, there'll be certain peaks, there'll be certain dips, it will not be always constant.
Yeah.
Right. So whenever you are dealing with renewable sources of input, renewable sources of energy, you should be ready to deal with non-ideality, you should be ready to deal with intermittent inputs, right?
Yeah.
Then you have to work on minimization of voltage flicker, because whenever you are using a supply with intermittent nature, okay, then the fluctuation will always occur in the output.
Yeah.
So you'll have to work on eliminating the voltage flicker. There have been different techniques in the history for mitigating voltage flicker. Like people used to use static war compensators and saturated reactors also, but that has been used in a large. There's been long time since people have been using those. Now new techniques have been developed. So then optimization of cost involved in mass production of the converter, fine. Then reduction of size of converter, because you have to work on reducing the size also. The size is a major issue, because if you are because it will be very easy to design a large converter, right? If you just take an example of a computer, personal computer. Earlier you had a cathode ray, the CRT monitors and huge CPUs, right? And then you have got miniature laptops and tablets. So if you want the same same configuration of PC, and you want to integrate in the laptop of small size, then the cost increases, right? Because you will have to design a highly integrated circuit, right? So the cost will increase. So you have to think on the optimization of all these factors, right? That the cost should also not be very high, because we Indians always concentrate on cost, right? So our cost should not be also very high, and size should also not be very large. So we want to optimize everything.
Yeah.
Then there should be improvement of efficiency, all right, because a non-efficient converter is useless. If you are not able to provide the required amount of power, required amount of output, then there's no use of designing such a topology, right?
That's true.
Then okay, now we talk about this passenger trains, right?
Yeah.
So first, before talking about passenger trains and coming to our main objective, I should discuss certain, I will. We have actually time, na?
Yes. We can.
How much time we have? Basically, can you give me an idea?
Yeah, we can discuss 20 more minutes.
20 minutes. Okay.
Yeah.
So I'll have to finish it fast.
Yeah.
So basically, I'll just establish a small background about the passenger trains.
Yeah.
So basically, in a traction load, like in a locomotive, there are several kinds of frictional forces, right?
That's true.
Like internal friction, external friction. We classified in 3 forms: internal friction, external friction, and air friction, right?
Yeah.
So in internal friction, there is the friction between the gears of the train, right? External friction is the friction between the railway track and the wheels.
Yeah.
And the air friction is due to the train is very large in size. So when it pushes against the wind velocity,
that friction.
The wind velocity and so there'll be air friction, right? So all this is called train resistance. So this train resistance basically contributes to the power requirements of the engine, right?
Yeah.
Your requirements from the supply. So okay, so there is one thing that is called the coefficient of adhesion. You have to coefficient of adhesion basically measures the slipperiness of the track. If you have got dew drops and everything, so it is right.
Yeah.
And if you've got sand and rust, then it will improve. The coefficient of adhesion will improve. So when we're talking about passenger trains, our converter, what will be doing that suppose you have got 10 sleeper coaches and 10 AC coaches. And the requirement is from a published report, right? And the requirement is approximately 261.18 kilowatt.
Okay.
So you are basically what we are doing is that we are providing solar cells on the roof of the train.
Okay.
Yeah, solar cells on the roof, and then we are providing battery banks within the train.
Okay.
Battery supply. Now we are still deciding that should we place it independently in different coaches, or should we place it in a simple master coach. So we are still deciding on the optimization of that. And then there will be n number of inputs. We'll inculcate different number of inputs, like one from PV source, then one from battery, then one from grid also. For now, we'll take from grid also.
Okay.
The 25 kV input that is taken from the electrical supply to the train, single phase supply, right?
Yeah.
So that will also be taken, and then there we'll be installing our MIMO converter, right? Multiple input, multi output converter, and that will cater to the requirements of the train. Okay. Whatever the requirements of the train are, that will cater. That our converter will cater to the requirements. So first of all, it will have all the advantages that I discussed about the MIMO converter, a centralized controller and everything. That converter will have everything. Along with the converter, we are giving a controller also. We'll design an intelligent controller. See, there are different types of controller, conventional controllers, like nowadays we have got intelligent controllers basically working on fuzzy logic, right?
That's true.
Like suppose you had earlier we had to like suppose you take an example of air conditioner, right? Now you are increasing its temperature from suppose 18 to 25 degrees.
Okay.
So it is sensing that either it is cool or it is hot, right? But sometimes it has to sense that it is somewhat cool, right? Somewhat hot. Okay. The requirement is not known exactly. It is fuzzy. Okay. So controllers are designed nowadays on fuzzy logic. Okay. So our controller will be intelligent controller. Now this is a diagram for the proposed converter. Right now it is a detailed diagram, if you can see it.
I can.
So basically we have got a 25 kV line here. If my cursor is visible, I'm showing
yes, visible.
Yeah. So your 25 kV 50 hertz single phase AC line. It is running, and then you are taking it through a pantograph. And then you are supplying it to a traction transformer. So the traction transformer is four windings are being given to the traction converters itself. Right, because the traction, you have to do the traction, right? You have got motors in the coaches. To make the train traverse its gradients, right? You have got motors. So in order to control those motors, you will be supplying them through a converter assembly. So for some of the supply is going towards those motors itself. So we are not meddling with that supply. Then some is going to the auxiliary windings. We are meddling with what? We are meddling with the supply that is given to the user in the coaches, right? Because we have requirements of single phase load, single phase AC load, three phase AC load. Like you have air conditioners in the train, right? So that's three phase AC load. Then there is single phase AC load and DC loads also, because you have got fans, and then you have got mobile charging circuits also in the train. Right, plugs. So you have different kinds of loads. So what we are doing is that we are taking here from the pantograph, we are taking a 960 volt single phase AC, then we are feeding it to the IGBT rectifier. It is AC to DC. Then we are inserting a capacitor, and then three phase IGBT based inverter. So it was basically single phase supply. We have converted into DC by a rectifier. We have filtered it. We have improved the output, and then we have converted into three phase, right? So then we have further improved the three phase filter. We have included three phase filter. And it will improve the supply further, and then three phase filter is supplying to a 750 volt three phase source to hotel load. And then that is given to the proposed power converter. That proposed power converter is also containing a DC battery bank input. And one from PV panels. Now PV panels itself are containing DC batteries, right? So these DC battery bank inputs, the second input, basically what you do, that suppose your train is reaching to different stations. Like you are traveling from Prayagraj to Delhi, right? And in the meantime, you are traversing across different stations. So suppose your train reaches from one major station to another major station and is stopping for suppose some time. So in the meantime, your train can charge.
That's
okay,
true.
the DC battery banks can charge at the stations.
Yeah.
Fine. And then a PV panel is already there, right? Because whenever you are installing PV photovoltaic cells on the roof of the train, so you are basically taking the energy from the sun. So initially, how you are totally dependent on the electrical supply, right? Now you are becoming partially dependent.
Yeah.
Now, one more thing we are doing in the converter, we are claiming in the converter is that we'll make it possible for n number of inputs and n number of outputs, right?
Okay.
So if in future, if somebody decides that no, we want to develop more inputs and we want to supply more inputs, then okay, welcome, develop. Okay. So our converter will be like this.
Okay.
Then further the objectives of the research proposal, right? So what we are doing is that we are developing a unique power converter that can take a different types of inputs and supply them to multiple outputs.
Yeah.
Okay, then we are designing an intelligent controller. Basically, I already told, on the basis of fuzzy logic.
Yeah.
And what it will do that it will optimize the power flow from different hybrid power sources to minimize the grid input supply.
Yeah.
And then the converter will be dynamically reconfigurable, right? What is the meaning of this? Is that suppose to maximize the output, right? What the converter will be able to do is that in the process of its on state, right? Like whenever you have switched it on, whenever it is functioning, it will be able to change its interconnections. Okay.
Okay.
Dynamically. Okay. So suppose in the series parallel interconnections within the converter, they will be able to change.
Yeah.
And it will change its topology design, and it will be able to provide you maximum output. Okay, so the nature of output and everything. So the converter, with the help of a controller, will detect which load requires what nature of supply, and the energy will be distributed accordingly, right? Because some loads will require AC supply, some loads will require DC supply. So our converter will supply everything.
Okay.
It will detect with the help of the controller.
Okay.
Now what we are thinking of doing is that we will try to incorporate WBG in the converter. WBG are wide bandgap devices, right? Because in the earlier slide, I discussed about silicon and germanium. I also told that gallium nitride and silicon carbide are being used.
Yeah.
So basically, what are wide bandgap devices is that they have wider bandgap between them as compared to the conventional silicon and germanium, right? The silicon carbide and gallium nitride, they have wider bandgap. So they have several advantages. The main property of wide bandgap device semiconductors is that they have higher bandgap. Okay, then wide bandgap based power devices are also enabling many emerging applications that were beyond the realm of SI. Because they can operate at higher whenever a higher power rating is there, they can operate at that also.
That's true.
So if you are making your power converters based on these devices, because power converters have switches basically. What are power converters? They are interconnection of switches. Okay.
Yeah.
So those switches are made by some certain semiconductor devices. Conventionally, they were silicon and germanium. Now we are incorporating gallium nitride and silicon carbide.
Yeah.
So we are taking the advantages of these modern WBG device semiconductors also. Okay.
Yeah.
So basically, these have already been applied in aircraft systems nowadays, in jet airplanes and fighter planes. I'd read maybe in USA or any other country, or maybe I am not sure of. So they've already started doing this, and maybe in India also. I have not studied the WBG application in detail.
Okay.
So so because we are basically focusing on the converter.
That's true.
This is a aspect that we are still thinking on, and if provided funds, we'll basically work on this also.
Okay.
So we'll keeping it in our hand also, this application also. Okay.
Okay.
So SiC based power devices are being tailored for power electronics from 900 to 15,000 volt and higher. Okay.
Yeah.
So see, I have simulated a small buck converter. Okay, just in order to show, in order to compare a WBG based device.
Okay.
In an actuality on a converter. So suppose this is a buck converter and it is using a silicon switch, right? So this is a 600 volt input, right?
Yeah.
And the load is 10 ohms and 500 millihenry inductor is being used, and the switch is U7. You can see here. and diode is D1N4002. 100 microfarad capacitor is being used. The parameters have been mentioned here: V1, V2, TD, TR, and pulse width and everything. So this kind of output is being obtained, right? Like the above the first here you can see the 600 volt output, right? Sorry, input. Green line shows the 600 volt input, and it is being bugged to about you can say 500, then 1, 2, 3, 4, 5, like 530 to 40, right? 530 to 40 volts. Now, if you are using, instead of silicon switch, if you are using a gallium nitride switch, the topology is the same, right? The topology is same. You have not changed anything in the topology. You have not meddled with the duty cycles also. Everything is same. The supply input is also same. The load is also same. At everything remaining constant, you are changing from 600 volts to about, you can say 100, 200, 300 to 400, between 300 to 400, like 350 volts. Okay. So see the ratio of bucking, right? Initially, with silicon, you were changing from 600 to about 540. Now you are changing from 600 to about 350. Okay. So this is the effect of gallium nitride. Okay. So these are the advantages of wide bandgap power converters, right? So lower size, lower weight, lower switching loss, lower conduction. So whatever disadvantage we are getting from the MIMO converters, right? We are eliminating it with the help of the WBG devices. Then if we are incorporating WBG in MIMO converters, then we are developing more, like we are doing a further advanced research. So basically, what our project is that first of all, we are providing it to the railways, that we are making it dependent on the renewable energy, right? So renewable energy along with battery bank and everything, and then we are proposing a new kind of converter that will be able to handle all kinds of inputs, and it will be able to supply all kinds of outputs, right? It will cater to the requirements of the railways, and in case of any other application also, not only the railways, like suppose powering a grid, like powering a small village, or maybe in electric vehicles. Different kinds of applications it can be used in. So that's what our project has been proposed about. And if anyone is interested, if any firm and organization is interested, that they can contact my supervisor. So I'll provide the details of the my supervisor and myself also. So he's Professor R.K. Singh. He's the senior member IEEE. Professor of Electrical and Engineering Department in MIT Allahabad. He's currently the Dean Academics also. And the email ID and phone number has been given, and here is my details. So if anyone is interested, they can contact us, and we'll be very happy to work on this, because we are interested in this research. So we have more ideas for projects, and if any firm is interested, they can contact us.
It's a wonderful project, Tuhinanshu. It has all the features. It is, it is going to be a big project, because it's involved with all the converters. So because the nature is like that, the project nature is like that: choppers, inverters, rectifiers. So all the things are involved in this converter. Hello, are you able to see me? So the converter has a lot of features. There are different features. So multi-input, multi-output. I also came across some of the firms who are involved in these projects. It's not like implemented, but they are in R&D stage, like that. So I think mainly, for example, the nuclear related, and in Tamil Nadu, and other Neyveli Lignite Corporation, and other some firms are there. So they are actively participating towards this as an environmental or climate change point of view. So initially they are also planning with a 1 kilowatt, something like that, like a small scale prototype. So that's already some works are there. So I will also try to engage different people with you, whoever like-minded people are there, whoever in this area are there. So the multi inputs, whatever you told, it's like a fuel cell, solar, PV, and everything. it can be wind also. Yeah. So I already have, I think we interviewed one person from Andhra Pradesh, Anantapur district, like that is about wind related. He developed a 5 kilowatt model, a virtual, I mean, the direct physical model, 5 kilowatt wind turbine. It can generate water as well as electricity also. So that model also there. I mean, so he also, so you also start gathering people and simultaneously gathering the resources. So that also will try. They also will be a part. Yeah, I will also try to give the contact details, and yeah, we will all together try to bring this project into the good scale. But this railway related, I think you have to work a lot for using this project in these railways. So the design and everything needs a lot of homework, I can say. So why? Because it is a complex nature. The system is like complex nature. So where the location of all the devices, because it has a lot of operational issues. Not only, I mean, you can't keep everything at a single place, the source and everything.
Yeah.
What happens now? So for example, if any disconnection is there, for example, sometimes dislogging of bogies happens. I mean, some bogies will be cut off due to some issue or somewhere. That is rarely happens. So sometimes it will happen, but intentionally sometimes it is required to cut off due to some issue. So it still needs to be, I mean, in each location, the source needs to be in each location, but control needs to be at a single point. So there are different case studies we have to study these things. You are able to know when you are going to, I mean, if any chances are there, you try to reach out to any railway bogie, I can say the workshop, wherever it is there. Try to engage with the people who are there repairing and everything they're taking place. So it will give, not only for you, it will give better understanding, so that the actual scenario you can easily grasp it, and after the better topology we can include all the features that is going to be a good thing in the coming days. Wonderful project. So this is your PhD project, right?
Yeah.
Okay. Yeah. So it's nice. Different. I mean, you need to frame the specification also. Specification of each items. Like for example, battery. Say how much battery size you are intending for. So what should be the rating? So what is the K? Like you already shown some simulation models.
Yeah, because see, if we are taking the battery size very high, right? If we are saying that, okay, we'll suppose you take an example of electric rickshaw, right?
Yeah.
Electric vehicle, a small electric vehicle. If you're saying that, yeah, we want to supply more we can simply use more number of batteries.
Yeah.
Just by supplying more number of batteries, why to use like you are using you're thinking conventionally, right? And you're just imagining that, yes, why not use more number of batteries? Then
it's
you have
difficult.
to think like, if not only it's difficult, like it will be so much heavy that
that's
it will
what
be
I'm saying. It
very lucky if the rickshaw
can
pull the batteries itself.
Yeah.
Right. So
yeah.
you have to think about everything, right?
Yeah.
So yeah,
it will take, I think, a lot of time and efforts also for you. And it's good if some couple of you are taking help from some couple of others for researching on these surveys like that. I mean, how currently trend is there, like that I can think of it. And so start summarizing the parameters. For example, if PV cell means so what rating? For example, if you have 5 kilowatt capacity of total setup, so what should be the individual contributions? So fuel cell means say 1 kilowatt, battery 1 kilowatt, and PV cell 1 kilowatt. So like the supply from the grid 1 kilowatt.
Percentage of contribution.
Yeah, percentage of contribution of each individual resources you have to keep in mind. And for example, the PV cell, that is going to happen 8 hours a day, like that. So in that and wind contribution may be a little bit higher sometimes. So all the contributions you have to take care, and when to cut off a particular load if it is not falling in the band. Maybe say you assign 20%, it is then reaching only 5% or 2%, you can cut off it. Sometimes it may be reaching 120, 130%. You can cut off that also sometimes, because all components are not designed. So a lot of controls are required. So yes, it is possible. it is possible. You can we can just start doing this, but it needs a lot of other contributions also. Like you told, some industries who are already there in these fields, who are providing services to these areas. So it's better if they come forward and working along with you. So it is benefited for them also, and the project, whatever you are thinking, it also can grow to the fullest. Yeah, it's a nice project, Tuhinanshu. So happy to discuss this.
Thank you.
So I'm so happy to discuss this project with you. Yeah.
Thank you.
Yeah, nice. So after, this is the starting of this project. So in later, maybe 2 to 3 sessions also, we can discuss in the next 1 or 2 years span. So based on the progress of the project, so how it is going on. So it is better to keep
sure,
session.
no problem.
Yeah.
We will be meeting, no problem.
Okay. Thanks a lot, dear. Thanks a lot. So
thank you.
We will meet in
thank you very
session.
much. Thank you.
Yeah. Bye.
Thank you.
Thank you, friends. Thank you. Thanks for watching. This is about this video on PhD project MIMO Converter, multiple input, multiple output converter, mainly for railways and other areas. We can use this project. Yeah. So if you have any questions or comments or anything, then do comment in the comment section. And if you're watching this video for the first time, then do subscribe to this channel so that whenever I'm uploading videos, you will get notifications. You can simply click and watch it. Thank you, friends. We will meet in next video. Bye.